Today, we're going to unpack the surprising math behind scaling things up. It's one of those concepts that seems super simple, but our intuition, well, it often gets it completely, totally wrong.
So let's kick things off with something we all love, pizza. Imagine you see an 8-inch pizza and a 16-inch pizza. The 16-inch one has double the diameter, so you should pay double the price, right? I mean, it seems perfectly logical, but this is exactly where our brain falls into a very common trap.
Yeah, it's not even close. You're actually getting way more than double the pizza, and today, we're going to figure out exactly why that is. So let's dive right in.
All right, so to really get our heads around this trap, we've got to rewind a bit and start simple. We're talking just one dimension, a simple line, or length. This is the foundation for everything else.
Okay, so here's the key idea you need to grasp, the common ratio. This is just our scaling factor. So if we want to make something twice as big, our common ratio is 2. If we wanted half the size, the ratio is 0.5. Pretty straightforward, right?
And you know what? Here, in one dimension, with something like a perimeter, everything works exactly like you'd expect. We double the sides, using that common ratio of 2, and what happens? The perimeter doubles, from 10 to 20. A perfect 2-to-1 ratio. So far, so good. No surprises here.
Okay, but now let's level up. We're moving into 2 dimensions, and this is where our intuition starts to go off the rails a little bit.
Think about it. We measure area in square units, don't we? Square inches, square feet. That word, square, is actually a massive clue for what's about to happen. And here it is. Here's the big twist. We doubled the sides, but the area? It didn't double. No way. It went from 6 all the way to 24 square centimeters. It quadrupled. That's 4 times larger. This is that scaling surprise in action. And that right there, that's our first big rule. When you're dealing with 2 dimensions, the increase isn't based on the ratio itself, but on the square of the ratio. Our ratio was 2, and what's 2 squared? It's 4. And that's exactly why the area is 4 times bigger. So, we've got the square rule down. You can probably guess where this is going next, right? Let's jump into the 3-dimensional world of volume and see if the pattern holds.
And just like square was our hint for area, what do we use for volume? We use cubic units, cubic inches, cubic feet. I bet you're starting to see the pattern now.
Whoa, okay, look at that leap. We doubled the side lengths again, but the volume, it just exploded. It went from 30 cubic centimeters all the way up to 240. That's not double, it's not quadruple, it's 8 times larger. And there it is. The pattern is confirmed. For any 3D measurement like volume, you have to cube the common ratio. Our ratio was 2, and 2 cubed, that's 2 times 2 times 2, is 8. This is the cube rule. It's why making a physical object just a little bigger makes it so much heavier. Okay, let's pull all of this together into one simple framework. Think of this as your cheat sheet for never falling into that scaling trap ever again.
This is it. This is the whole thing in a nutshell. For 1D stuff like length, the ratio is just, well, the ratio. For 2D area, you square it, and for 3D volume, you cube it. It's that simple, and it shows you how that effect just grows exponentially as you add dimensions.
So this is all cool math theory, but what about the real world? Well, you use this stuff all the time, maybe without even realizing it. Let's run through a couple of common examples and see how it works. All right, first up, let's say you have a 3x5 photo, and you want to enlarge it by 150%. What are the new dimensions going to be? How would you figure that out?
Well, once you know the rules, it's actually pretty easy. First, you just turn that percentage into our common ratio. So 150% becomes 1.5. And since the dimensions, the sides, are just length, that's a 1D problem. So we just multiply each side by 1.5.
And boom, there's your answer. The new photo is 4.5 by 7.5 inches. And just for fun, think about its area. It would be 1.5 times squared, or 2.25 times larger than the original. See? The rule holds up perfectly.
Okay, here's a classic one you might have even seen in a math class. You've got a student who is 5'6" and casts a 6-foot shadow. At the same time, a tree nearby casts a 20-foot shadow. How in the world do we figure out how tall that tree is? The key here is that the sun's angle creates 2 similar triangles. That means the ratio between their shadows is the exact same as the ratio between their heights. So all we have to do is find that common ratio by dividing the shadows, and then just apply that same number to the student's height.
And we find out the tree is just a bit over 18 feet tall. It's a perfect example of how these simple rules of ratio and scale are at work all around us, from the photos on our wall to the shadows on the ground.
So now you've totally got the math down for shapes and objects. But it gets you thinking, doesn't it? Where else do these scaling laws pop up? Not just in geometry, but what about in business or in nature? If you double the size of a team, does the complexity of their communication quadruple? It's a fascinating question, and it just shows how powerful these simple mathematical ideas really are.